Welcome class. Now I am going to start that next hydrotransfer reagent, that is on Dibal H. So previous class I have discussed on the hydrotransfer reagents, like first is lithium aluminum hydrates, and I also discussed about of that NaBH4. So third hydrotransfer reagents, now I am going to discuss, that is Dibal H. So this Dibal H is compared to that lithium aluminum hydrate, this is called a less reactive reagent. It means that whenever any reagent, if it is less reactive, it means that in other side it become the more selective. So Dibal H compared to lithium aluminum hydrates, it is less reactive. It means that it is more selective than lithium aluminum hydrates. So that point you should be always remember, that if any reactions become a less reactive, means at the same time it become that more selective. So what is actually a Dibal H, and how its structure and how its functions, where its applications is, and what type of solvents we will use, that whole details we will discuss today. And also we will discuss that what are the selectivity of this Dibal H, means why you are using this Dibal H, why you are interested about of this Dibal H, because lithium aluminum hydrate is already present. This is also hydrotransfer reagents. NaBH4, this is also hydrotransfer reagents. But why you need another hydrotransfer reagents, Dibal H? So that detailed things we will discuss today. So let's first discuss about that what is the full form of Dibal H. Here we are seeing that Dibal H. So this Dibal H is actually the diisobutyl aluminum hydrate. Dibal H also called the diisobutyl aluminum hydrates. How the structure is? So if I talk about the structure of this Dibal H, so you see that diisobutyl aluminum hydrates. So aluminum hydrate, it means that aluminum is there and hydrate is there. With that diisobutyl means that isobutyls will be there. This is one isobutyl, that two isobutyls will be there. Okay, so this is the structure of diisobutyl aluminum hydrate, means that one isobutyls, another isobutyl, two isobutyl with that that LH bond will be there. So this is the structure of Dibal H. So like I have already discussed that boron families, boron and aluminum, these are the electron deficient groups. Electron deficient groups, so they actually have that valence electrons 3. So with that 3 also they are octet incomplete. So this aluminum also same, that 3 valence electron there. After sharing all the valence electrons, still it become a electron deficient. So these are all under in electron deficient groups. So now what the interesting things if they are electron deficient groups? Okay, so what we see that this aluminum hydrates, this is the electron deficient groups. So whenever any groups is electron deficient, it means that is a Lewis acid. So we know that Lewis acid means they are accept electrons. So this is also a Lewis acid because 2 electrons are needed to complete its octet. So to get it stabilized, it means that this accept electron, it means that this is also a Lewis acid. The interesting things what is there, let's say if you compare about of that Dibal H, lithium aluminum hydrates and Dibal H, then what we see the interesting things, see that lithium aluminum hydrates, that is this and this Dibal H. So how that it is, here lithium plus, and here we have that AlH4 minus. Similarly, the dival H is, this is AlH is there, and that two isobutals are there. Okay, so this is the structure of this, and what you see that here, if I draw this, then this Al and one hydrogens, another hydrogens, another hydrogens, and another hydrogens. It means that here we see that 4 ALH bond is there, but here only one ALH bond is there. So what we notice here, that here we have 4 ALH bond, and here we have that only one ALH bond. And since it is a hydrate transfer reducing reagent, it means that H minus we will get from here. What you get, that H minus, here also you get that H minus. This H minus will do the reactions. So the H minus we are getting that from this 4 hydrogen atoms, means that from these 4 ALH bonds we get that, means 4 H minus here we will get. The availability of H minus is 4, but here the availability of H minus is only 1. Okay, so this is the basic difference between ALH, dival H and lithium aluminum hydrides. And the next differentiation is what you see here, that here that lithium aluminum hydride, this is a Lewis acid. It means because this is a electron deficient groups, because Li plus, okay, metal with plus charge, so this is a Lewis acid. So this Lewis acid, and what we see that here we see that ALH, this is the negative charge, because these aluminiums will have that if you look, it's that valence electron, it has only 3 valence electrons, so with 3 it will do that 3 bond with H. Now another if now this is a 6 electrons, so this is the electron deficient groups. Whenever it gets another electrons, let's say another ALH bonds, whenever it get another hydrogen bonds, it become a negative charge. So as soon as it get a 4 bonds, it means that 8 electrons, octet completed, it become a highly reactive, because previously it is electron deficient groups, and whenever it get one more bonds, it get very highly reactive, and it easily donate that this LH bonds. So this electron deficient groups, they will donate hydrates only when they have that octet is completed. After octet completed, and then only they will donate that hydrogen atoms. But now we see here, in this case, how many bonds are there? 3 bonds, means here only that 6 electrons is there. For octet completed, 8 electrons there. So now it can't donate this ALH bonds, because this electron deficient groups, they will donate the hydrogen bonds only if they have the octet completions. But here is octet is not completed, 6 electrons. So what it will do, that it will act as a Lewis acid. For this case, lithium plus was acting as a Lewis acid, but now here this compound itself acts as a Lewis acid, because it need electrons. For this case, this lithium need electrons, this not need electrons, because this is already become electron rich and it is ready to donate that hydrate. Okay, but here this, since octet is not completed, so it can't donate. So now at first it will act as a Lewis acid, because octet is not completed. So now if it get another bonds, let's say if you have this carbonyl groups, then this oxygen has the lone pair, and this oxygen if donate it to this aluminum, then what we will see, that ALH, let's say after that H, now let's say that it donates with that this donate with oxygen, and oxygen get the positive charge, and okay, so because this oxygen give the lone pair to this to this aluminum, so this get a delta positive charge. So now after that what happened, that it get that 8 electrons from 1 2 3 4 5 6 and 7 8, because it giving the 2 lone pair electrons. Now it get that After that, this become a negative charge because octet is completed. Now it will donate the electrons. It means that lithium about this Dibal H, what it will do? It will first act as a Lewis acid. After Lewis acid, then only it get octet completions. After that only this ALH means hydrogen transfer will occur. Unlike here no need to act because Lewis acid, this Li plus is already a Lewis acid, and this is already a octet is completed. So now this is ready to donate that hydrogen atoms. But in this case, first it will act as a Lewis acid. After that, when it's octet completed, then only this is ready to share this hydrogen atoms. So this is the basic difference between the lithium aluminum hydrates and that Dibal H. Another thing is that here we have that 4 hydrogen atoms, here we have only 1 hydrogen atoms. It means that from this 1 hydrogen atoms, because it become a selective to the reactions with the reactants, because it have only 1 hydrogen atoms with that bulky groups are there. So it makes it's a selective to that reactants, unlike these lithium aluminum hydrates where these all are that less bulky groups and 4 hydrogen atoms are there, and it become a very reactive. But here only 1 hydrogen atom is there, so it become a less reactive compared to this lithium aluminum hydrates. With that, it has a bulky groups, which also helps to become it's a less reactive, which means it become a more selective. Okay, so these are the basic difference between that lithium aluminum hydrates and Dibal H. Now coming to that, what type of solvents we will take for these reactions. So you see that for lithium aluminum hydrates, we generally take the solvents that is, since this is a highly reactive, so this actually if we give the polar solvents like water or alcohol, then it will react with the solvent. So we used to take that aprotic solvents like PHP we used to take for lithium aluminum hydrate, aprotic solvents. But for the case of this Dibal H, since it become a less reactive because of its structure and its bulky groups, it become less reactive. So here we take that range of solvents. Also this Dibal H, what you see that this Dibal H is found in a liquid. Okay, so this Dibal H, because you see that lithium aluminum hydrate that is found in a solids, but this Dibal H will see it is found in a liquids, and that liquid is soluble with many solvents. Why you are actually taking the solvents? Solvents you are taking such that our reagent will be soluble with that solvents, first thing, and that our reagent should not react with the solvents. Okay, so why you are taking the solvents? For any reactions, for any reagents, solvent is taken. You say that what characteristics of solvent needed for a reagent to use the reactions. So what are the characteristics of the reagent? One characteristic is that that our reagent should be soluble with the solvents. So first is that reagent should be soluble with solvents. This is the first characteristics, and second is the most important, that is reagent should not react with the solvent. And third is that that is also needed, that the solvent should be easy to, after completion of reaction the solvent need to be separated, so the solvent should be easy to separate from the reactions mixture. So these are the some characteristics are needed to use the solvents for a particular reagents in a reactions. Okay, so these are the main points. Some other points also we'll see. Okay, so what type of solvents you will take for the Dibal H? Since a Dibal H is found in a liquids and that liquid is soluble with many solvents, so the solvents we will take for this case is like we can take solvents solvent needed for reagent Dibal H. Or what type of solvents we need? Firstly, the solvents like we can take that diethyl ethers, diethyl ether. The taking of this is that diethyl ether has that lone pair, so that will do the reaction, that will share this lone pair electrons to this Dibal H, so that this will be some that it will make a bonds coordinate bond, and that is adduct. After that, that will be soluble. That okay. So that is the main reasons we take diethyl ethers. Also, that will not react with the reagents. So diethyl ether we can take. We can take that DCM, and we can take the solvents like DCM means dichloromethanes, and also so many reagents we can take that THF. So this type of reagents we can take for the Dibal H. Okay, so now this Dibal H is become more like lithium aluminum hydride. The same characteristics, same ALH bond is there here also, and we see that ALH bond. So what we have seen here, this ALH bond. So this is you see that this is 3s 3p and this is 1s. So the size difference is there. Size difference is present, so it become a more reactive. So here also the likewise in that lithium aluminum hydride we can't use that water and alcohols, okay, because this is highly reactive. So solvents like water and alcohols are not used, because it will react with that this water and salt alcohols, because that ALH bond is a very reactive because the size difference is high. Okay, so this type of solvents we avoided while taking the Dibal H reagents. These are that what type of that structure is, and why what type of solvents you will take. Okay, so what you say that Dibal H, it is a strong reducing reagents because ALH bond is there. With that, this is a bulky reagent because 2-isobutyl is there. Okay, so it makes it a more selective and less reactive than lithium aluminum hydrates. So now that if I talk about of that reactions wise, this Dibal H, so what the Dibal H will do that if we have that the groups like esters. Actually, this Dibal H, it is preferred. It is mostly used for the reduction of esters and nitriles to aldehyde. Okay, so this Dibal H is mostly used in the labs to do the reductions of esters and nitrates to aldehydes. Like I said that this Dibal H is more sorry less reactive but more selective. So like we have that lithium aluminum hydrates. If we are using that lithium aluminum hydrates, let's say we have that ester groups, and here if we are using that lithium aluminum hydrates, then what we see that this is directly converted into that alcohol groups, 1 degree alcohols. And if you have that nitriles groups and you are using that lithium aluminum hydrates, then what it will do, that it directly convert into that 1 degree amines. Okay, means from ester to directly it convert into the 1 degree alcohols. But now same category of this lithium aluminum hydride, same ALH bond is there, but with that we, what we say that we add that bulky groups like diisobutals. That means that Dibal H we are using, if we have that ester and now we are using that Dibal H, then what will happen, that this ester is converted into that aldehyde. It means that it will partially reduced from ester to aldehyde, means partially reduced. Partial reduction, why I am saying that, if you are doing ester, then it is directly converted into this 1 degree alcohols. But if we are using Dibal H, then it will reduce to aldehydes. It will not further reductions, it will not do further reductions to alcohols. It stop at to aldehyde stage. It will not do the further reductions to 1 degree alcohols. It means that it will do the partial reductions of ester. Okay, it means it is reducing from ester to aldehydes. It not reduced to 1 degree alcohols. Similarly, if you have this nitriles and if we are giving the Dibal H, it will convert into this amine, and after that if you do that hydrolysis, then it will convert into that aldehyde groups. Okay, so this is that advantage of this Dibal H, that from ester to it will convert into the aldehydes, and from that nitriles it convert into amines. After hydrolysis we will get that aldehyde groups. It means that if you want to get aldehydes from esters, then you will use that Dibal H, which will stop at the aldehydes. So it actually what that save the times, save one stage of reactions. Like if you have that ester, you take that 1 degree alcohols, and if you want to go to the aldehyde, again you have to do that oxidations with that mild oxidizing agent, like you has to use that PCC, or we can do that SORN oxidations. Then we get 1 degree alcohol to you can get that aldehyde. It means that while using this Dibal H, we will save that one stage reactions, means time consumptions with reactions with that time consumptions will be happened, and with that what we no need to do one more step reactions we no need to perform. So that's the why that Dibal H become a more important for this case. It means that it will stop at the aldehydes from esters. But if we use at the same time lithium aluminum hydride, directly convert into 1 degree alcohols. From that again we have to use some that mild oxidizing agents or SON oxidations to get aldehydes. Similarly for nitrates, if you are using that lithium aluminum hydride, we are getting 1 degree amines. But if you are using the Dibal H, then we will get amines, and hydrolysis we will get that aldehydes. So this is the regions the Dibal H become important reagents. Yes, that is the step that we have to maintain that low temperature, and in that lab it become little bit complicated that we are getting aldehydes. So but yes, you get that aldehydes, but if you are doing the performs in the labs, it may become little bit complicated to separate these aldehydes. But yes, we will get that from ester to we get aldehydes, and from nitriles also we will get that aldehydes. Okay, so these are the important things why you are using this Dibal H instead of lithium aluminum hydrates if you are want to get esters to aldehydes or nitriles to aldehydes. So if you see that reactions mechanisms, So if you see the reactions mechanisms, how this converted is to aldehydes, convert nitrates to amines. So let's talk about other mechanisms, how it will follow. Suppose we have that ester groups, like if we have that ester groups, HCO. So if you see that mechanisms, let's say this row ester groups. Now if we are giving that Dibal H, then what will do that? Dibal H, it means that we have that aluminum hydrogen bonds, here we have that isobutane. So here this is the Lewis acid part, it will say after the Lewis acid, it means that it has that vacant orbitals is there. So now what will do that? These oxygen atoms will give its lone pairs to this. Also we say that here also lone pair is there. So why it will not do from here? The reason is that here that after doing the reactions it become a 3-degree carbohydrate. Let's see how it will. RCO. Here we have that aluminums and here we have that isobutals and here we have that hydrogen atoms. Okay, now to get that negative charge become the octet is completed and this is become an electron rich group. Now what it will do that, and here we have that groups for CH3. So now what will happen that these bonds will attack to this polar charge, because after that this is also getting a delta positive charge because it's giving a electrons to lone pair electrons has gone here, so it will get positive charge. So electronegativity atoms get positive charge means it abstract electrons, so it here will get the delta positive charge. So due to that this edge will attack here. Now what will do that, then this see this bond will remove here and positive charge is gone. Okay, now here we have that this hydrogen atoms come here and here we have that OCH3. And now it becomes that Al. Okay, this type of bonds. So again it become a 3 bonds it have. So now what we will do that hydrogen atoms is not present. Now we will do that hydrolysis. If you do that hydrolysis, so acetic hydrolysis we will do. Okay. Yes, one more thing is that see here that after it will goes here. Now this OCH3 become a good living groups. So it will remove here because OCH3 is a good living groups. Okay. Now if we give that hydrolysis, let's do that hydrolysis. Then what happened that this bond will break and this will come here and this is a good living group, so this will be, it will become that RCOH. Aldehyde groups will get. So this is the mechanisms that follows that if we have the ester groups, then it will convert into that aldehyde groups. Similarly, if we have that nitrile groups, let's say RC triple bond N, and you have your Dibal H, that is aluminum and hydrates, and that isobutals are there. Okay, so now it has the lone pair, this nitrogen, so this will donate to this aluminum. So what happened that RC triple bond N and here we have that aluminums, hydrogens, and isobutane is there. Now it get the negative charge, and since here that lone pair has gone, so it get a positive charge, so it abstract electrons from here, so it get delta positive charge, and this will attack here, and this will remove like this. So what we get here, that R C, so one bond is gone here, and here we have that H, and here we have that aluminums, and here we have that isobutane group. Okay, so now it becomes, this is the amine. Now we have to do that hydrolysis, any acidic hydrolysis. If you do here, then what will happen, that here we will get that instead of this we will get that this will remove, and to water to the oxygen will come here. It means that it will get that R C, this N will go, and here you will get the double bond, and this is the aldehyde group first, and it's good. So again we will get that aldehyde groups. Yes, here we don't need to do that hydrolysis, because directly what we see that this will go here, and this will remove, because this is a good living groups, and again we will get that same, that ALH bonds. Okay, after that what you will see here, this Al isobutyl groups, and here this OCH3 is there, its lone pair will share with this. Okay, so this aldehydes will get here. Here we don't need to do hydrolysis to get aldehyde groups for the case of ester groups. And for case of nitrates, we have to do that hydrolysis, because first we will get that amine groups. From amine, if you do that hydrolysis, then we will get that aldehyde groups. Okay, so these are that mechanisms for how we will get from aldehydes to sorry, from ester to aldehydes, and from nitrile to aldehydes. But that most important thing is that here we have to maintain the temperature. For this case, the temperature should be minus 70 degrees centigrade, or that is minus 70 degrees centigrade. Then only we get that aldehyde groups. Otherwise, it will further reduce to that alcohol groups. So important thing is that if you have ester groups RCO, OCH3, now if you are giving that Dibal H, and if the temperature is 70 degrees centigrade, then we will get that aldehyde groups. But if we are giving this Dibal H and temperature is not mentioned, means at normal temperature it will convert into that that alcohol groups. Okay, so the temperature is important here, that whenever you are doing from esters, if it is temperature is minus 70 degrees, then we will get that aldehyde groups. Otherwise we will get that alcohol. Okay, so the temperature has to memorize that if the esters we are getting Dibal H with minus 70 degree or something, that 70 degrees centigrade, minus 70 degrees centigrade, then we will get that aldehyde groups. Otherwise, if temperature is not mentioned, at the room temperature, normal temperature, we will get that alcohol groups. So this is that important points for the case of ester. Similarly, for if you are doing that case of, if you are doing that acid chloride also, here you are doing that Dibal H, and if 70 degrees centigrade, then we will get that aldehyde groups. But if you are doing here with room temperature or normal temperature, then we are getting again that alcohol group. So temperature becomes a crucial role, like if, for Dibal H. Okay, so the temperature is very important. So if temperature is minus 70 degrees, then we get that aldehyde. If temperature normal, then we get again that alcohol. Okay, This may be the acid chlorides or the same things with amides also, RCO, NH2 or NR2. Here also we are doing that Dibal H, and if temperature is minus 70 degrees centigrades, then you will get that aldehyde groups. But if it is room temperature or normal temperature and we are doing that Dibal H, then what we get that? We get that like amines, 1 degree amines we will get. Okay. So that that temperatures play crucial roles for Dibal H, because what is it that at high temperature it will directly convert into that aldehyde groups, same way like lithium aluminum hydride do. Okay. So that temperature have to be look carefully while you are doing that Dibal H. The that temperature should be minus 70 or minus 70 degrees centigrade. Then you will get that aldehyde groups. Okay. So it should be always memorized that temperature should be minus 70 or minus 70 degrees centigrade. Okay. So this is the one point. Also that Dibal H, what will do that? If you are using the Dibal H, suppose if you have that alkyne groups, that is internal alkynes, not external alkyne or not terminal alkynes. Like here we have that C, and if we have that these R groups, and now we are giving that Dibal H. Okay. At any temperature, at room temperature. So if you are giving this is a internal alkynes, then what will do that? It will convert into that cis alkenes. Means that double bond of C, here will be H, here will be H, here will be the R. Let's say this is R and this is R test. It will convert into the cis alkenes. Okay. That should be the internal alkenes. Okay. If it is like CH, RC, triple bond of CH, this is the terminal alkynes. Terminal alkynes. In this case, if you are giving the Dibal H, then there will be no reactions. It means that has to be that internal alkynes, then it will convert into the cis alkenes. If it is a terminal alkane, then there will be no reactions. Okay. So this is the important points for that Dibal H. That is, first point is that it will convert into that aldehyde groups from ester or from amides or from chlorides, acid chlorides. It convert into the aldehyde groups. But important thing is that the temperature should be minus 70 degrees centigrade. Okay. But if you are giving a room temperature, then that again that convert into that alcohol groups like lithium aluminum hydride. Okay. So this Dibal H will helps us to protect or to consume that one. It helps to time saving. Why? Because we don't need to do one more steps like from if it convert into alcohols, then again we want to do aldehydes, then we have to do one more reactions, that is from PCC or from soil oxidations or mild oxidizing agents we has to give to convert into aldehyde groups from alcohols. Okay. So these are the points. Okay. So these are the points that is needed for that Dibal H. And one more point. हेलो हाँ बने हाँ नमस्कार हाँ हाँ तो रख लिया Okay, so that is the points. And one more things that is needed, that is we see that that esters, and yes, if you have that aldehyde groups and ketone groups and ester groups, suppose in a reactions if you have both aldehydes, ketones and ester groups, then Dibal H will not selectively react with esters only. Like if we say that if we have that any groups, let's say we have that O, and here we have, let's say we have that, so here we have that both the ester groups and both that ketone groups. This is the ester groups and ketone groups, both are present, and you are giving the Dibal H. Then what will do that, it will react both of them. It will not selectively react on the esters, it will react both that ester groups and ketone groups. Means that it will react with CH2, this is also converted into that aldehyde groups, and if a ketone, then it will convert into that alcohol groups. It means that CH2. Okay. So it will react both esters and ketones. It not selectively react on the ester. If it is ketones or if it is aldehydes, then it will convert into that alcohol. So that this is the one demerits of that Dibal H. It not selectively react esters. It react both ketones, aldehydes, and esters. Okay. So now we will look some questions and answers to bind up the classes. Okay. So first questions will be, we have that example one, like you have that ester groups. Okay. Now we are giving this Dibal H. Then and temperature, you has to look the temperature -70 degrees centigrade. If it is a like room temperature, then this will convert into a alcohol group. So it will not stay at the aldehydes. Okay, so the temperature is very important. So if you have the esters, then it will convert into that. You look that the temperature. Okay, -70 degrees centigrade. So this will convert into the aldehyde groups. Okay. Now similarly, if you have the nitrile groups, and here that this hydrolysis is not needed, and now here also this Dibal H, this is that nitrile group, so this again convert into the aldehyde groups. Means that it will convert into like this aldehyde groups. So now again we have that, so Dibal H amines and DCN. So we say that that this is the solvents. Okay, so that's why I always discuss that what type of solvents that is used, because sometimes that by giving the solvents it try to make confuse. Okay, so that's why I'm discussing every reagent what type of solvents that can be used. Okay. So for Dibal H, -70 degree and DCN, this is the solvent. So at this is the ester groups that is converted into that aldehydes. This is ether groups, ether group will not get affected. So it will convert into, so this remain as it is. Aldehyde groups. This is convert into the aldehyde groups. Do here. It will not affect it. Ester groups, ether groups, and this will convert into the aldehyde groups. Okay. So similarly, if you do these reactions here, the Dibal H and DCM, and if temperature is not mentioned, then this is a room temperature, then it will convert into that alcohol groups, not aldehyde groups. Okay, so this will not get affected because this is the ether groups. Okay, ether group will not affected by lithium aluminum hydride, Dibal H. The ether group will not get affected. That remain as it is. H2H. Okay. Now here again that Dibal H is there, and this is the bond. This is the protecting group that we discussed later. And now this is the very important because this is the activated ester. Activated ester. If activated ester is given, if it is a room temperature, or it is a if it is a minus 70 degrees centigrade, or if it is a room temperature, both the case it will convert into that activated ester is converted into that alcohols, not into the aldehyde. If activated ester means it will become a more reactive. On that case, it will not stop at the aldehyde. It will convert directly to the alcohol groups. Okay, so now it will directly convert into the alcohol groups, not stop at the aldehyde. So this has to be remembered that if it is activated ester means that conjugation is there. Actually, how these molecules look like. CO. So this is the in the conjugation is there. So it will directly convert into a alcohol groups. It will not stop at the aldehydes. Okay. If it is activated ester. And rock. It will convert into the alcohol groups. Okay. It will not stop at the aldehyde. It will directly convert into the alcohol. If it is minus 70 degrees centigrade or it is room temperature, same product we will get. Here also the same product. If it is activated ester is given. Okay. Similarly, now the next question is then that if it is a internal ketone, internal alkyne. Okay, because this is internal alkyne, and if you are given Dibal H, then this is converted into the cis alkanes. Okay, so this is going to be cis alkane, that is R dash, and here also R, then here H, here H. This is converted into cis alkanes. Now, if you are giving that Na liquid NH3, on that case, that this reagent we will discuss later. That if the sodium and liquid ammonia if you are giving, then this is called that batch reductions. On that case, it will convert into the trans alkane. R dash and H, and here it will become that R and H, cis alkane. So you have to remember that Dibal H, cis alkanes, and sodium and a liquid ammonia will get the trans alkanes. Trans alkane. Okay. Now the same things that if you give here, you also will get that trans alkanes. Okay, so this will be the here will be the H, here also will be the H, and we will get the cis alkane. Okay, so today up to this, we will discuss in the next class with one more reducing reagent, that is hydrogen transfer reducing reagent, that is L selectrides or K selectride, that we will discuss in the next class. Today up to this, thank you.